Welcome to MET 200 Manufacturing Processes and Materials. This is Dr. Hamid Isa Sadeh. In this lecture, we will look at plastic forming and shaping, which is chapter 13 in the book. In this lecture, we try to cover all of this topic as much as possible, but because we have a limited time, we cannot address all of them one by one. So it is your responsibility to review the remaining topic that I do not cover in this lecture. Plastic can be shaped into a wide variety of products, like molded parts. It can be extruded sections, film, and sheets. We can make insulation coating for the electrical wires. We can make fibers for the textile. Also, plastic are often used for the principal ingredient in other material, like paint, adhesive material, um, matrix composite. So this is the dominant part in the composite. The, the dominant part is the polymer, and we have some ingredient that makes the composite more stronger. Application of plastic products have been increased recently, very high rate, and the rate is more than metal and ceramic. It happened around 50 and or 60 years ago, and many of the products that were used to be made of metals or ceramic, now they are made of plastic. Some examples are plastic containers, bottles, jars. These are made of plastics these days. In general, the total volume of polymers, which include plastic and rubbers, now it exceeds that of metal material. The question is here, why the plastic shaping process is important for us. There are several reasons. First, we have a variety of shaping process for the plastic, which makes um, the geometry for plastic unlimited. We can make a different geometry for plastic material. For example, we have many plastic parts formed by molding process. And molding is a net shape process. It means that further shaping is not needed. The next reason is that we need heating in the plastic shaping, but that heating is much less comparing with the metals, because metals requires a lot of energy to melt the metal. For example, if you look at aluminum, we have to heat up the aluminum up to 600 degrees Celsius. But for plastic, you can have a lower temperature, maybe 100 degrees Celsius or 150 degrees Celsius. Next reason, finishing by painting or plating is not required for plastic material. There are some circumstances that we need some painting, but generally painting is not required for the plastic material. In chapter 8, we talked about two types of plastic. Actually, we talked about three types. We had thermoplastic, we had thermoset, and rubber material. But here we are looking at two types, thermoplastic Thermoplastic has chemical structures that remain unchanged during heating and shaping process. And this type of the plastic comprises about 70% of the total plastic tonnage. The next type is a thermoset. Thermoset undergoes a curing process, um, and then it makes a permanent change in molecular structure, and we talked about it. It's called cross-linking. Once thermoset cured, we cannot remelt it. The first step in polymer shaping is to heat up the polymer or the thermoplastic polymer. Then it becomes fluid, and that fluid or liquid state, it becomes very consistent throughout the material, and it is called polymer melt. The polymer melt has two properties that we need to consider in the design. One property is called viscosity, the other one is called viscoelasticity. The viscosity, one good example is to look at the shape of ketchup sauce, or you can also see Pepsi. These two liquid material, they have different viscosity. So this one is very viscous. I mean, the ketchup, the viscosity is very high, and because it flows very slowly, right? But the other one, Pepsi, it has less viscosity. It's more fluid. Um, so the viscosity of that Pepsi is lower than the viscosity of the ketchup sauce. Viscosity is a fluid property of a polymer, and that is related to shear stress to shear rate during flow. When the polymer melts, because of its high molecular weight, it becomes very thick fluid. Thick fluid means high viscosity. And in the shaping process, polymer shaping process, if we have a lot of a small channel during the process, or the die opening might be so thin, so small. Because of that, material have to be thin to pass through those channels. And the good thing about polymer is that they are pseudoplastic fluid. As you see in this figure, the viscosity of the polymers decreases as you apply pressure on the polymer. The viscosity comes down, so the material becomes thin, so it can pass through small channels. If you apply high pressure, those material can go through some small hole. But we have some material that if you apply pressure, they become thick. But the polymer, we have this behavior. So the viscosity decreases as you apply pressure, or you have the shear rate goes up. Okay, and this is one benefit. And this behavior is called thinning property. Also, the viscosity changes over temperature. Here we have the plot that shows the viscosity of the various material like acrylic, nylon. For example, if you see nylon, the temperature as increases go this way, the viscosity comes down, right? So viscosity decreases. And same thing for other polymers in this slide. Another important property is called viscoelasticity, and this is another property of the polymer. A good example to describe this property is Dicewall. Here we have one Dicewall here in the gray color. The material are entering into this orifice, and they will leave on the other side of it, at the other side. This is very similar to extrusion process. This phenomenon can be explained in this picture, because you see when the polymer enter into this orifice, it becomes narrow, but during leaving, you see the polymers tend to come back to its former shape, and it attempts to return to that shape when leaving that die orifice. So the material remembers their original shape. This is called viscoelasticity. Okay. Another way to say it is it has a memory. The first process of the shaping polymer is called extrusion. In the extrusion, we have a polymer that is going to be forced to flow through a die orifice here to provide a long product, and the cross section of that product will determine the shape of this orifice at this part. And this technique is widely used for thermoplastic and elastomers for mass production, like pipe production or structural shape production, and etc. And because we have a continuous process, this extrudate can be very large, as much as you need. And if you want to cut it, then they have a cutter device located on the right side of this machine to cut that extrudate into desired lengths. Here are the component and feature of the machine. In the next slide, we'll talk about all components one by one. The extruder has two main components. It is called the barrel, which is this area, this section. Let me erase this part, then draw it again. This area is called barrel, and then we have another important component. It's called a screw, this one, which transfer the plastic material to from left to right. And die, which is located here, it's not an extruder component, and this die can be replaced, and we can place a different die for every component depending on the application. So we can design a die and put it at this side of the machine and make a different profile, different products. And here one more thing, you see it has different part. It's this from here to here, it's called feed section. Then this area is called a compression section, The last part is a metering section. The extruder barrel has the internal diameter, and that diameter can be between 1 inch and 6 inch, or between 25 millimeter up to 150 millimeter. And the length over diameter ratio can be between 10 to 30. For a higher ratio, like a 30 ratio, that is mostly designed for thermoplastic material, and if it is a low ratio like a 10, that is designed for elastomer material. In this picture, as you see, we have pallet in the hopper, and that is going to be moved toward the screw by the gravity force. And here we have a heater that melts the feedstock, and this screw push the material toward the die orifice. The extruder screw has different sections. Feed section, it has a compression section. In the feed section, the feedstock is gonna move from hopper, and then we have some preheating over there in this area. And then we have a compression section. The polymer is going to be transformed into thick fluid, and air is going to be mixed with the pallet, and then it is extracted from the melt. Then the material, or that polymer, will be compressed at that area, this compression section. In the metering section, the melt is going to be homogenized, and then we have sufficient pressure to pump the polymer through the die opening, this part. So the metering section is this area. As I mentioned before, the shape of die orifice is important, because that is the component that determines the cross-sectional shape of the extrudate. And we have some common die orifice. For example, we have a solid profile. If we have a hollow profile, that can make tube. We have wire and cable coating. We have shape die orifice for sheet and film, and there are some die orifice to produce filaments. Extrusion of solid profiles include regular shape and irregular shape. In the regular shape, we have round and square cross section. For the irregular cross section, we have a structural shape. It can be door, window, molding, automobile, air trim, and housing, siding. In this picture here, we see the cross section of the extrusion die for a solid regular shape. On the right picture, we see the front view of the die with profile of the extrudate, right? And the end of the screw, which is here, we have a screen pack and breaker plate. This part of the die, the machine. The main reason to have the screen pack and breaker plate is that to straighten the flow line, and the polymer melt flows into the conversion die entrance, this part. Then the shape that is designed before it will this profile, this area. it will maintain a laminar flow and it avoid a dead spot in the corners. And finally, it leaves the machine. We also can make hollow profiles in the extrusion process. Here are some examples. As you see, we can make tube, pipes, hoses, and also we can create other cross sections that contain holes in them. The hollow profile require a mandrel, so that is important. So the mandrel is going to be used to form their design shape. As you see in this picture, it shows the extrusion die for a hollow cross section, and the AA section AA here is a front view of that mandrel and how the mandrel works. So the mandrel is held inside this cross section, and then it blows air to form the designed cross section. Normally we use air to maintain the hollow form for the extrudate, and the left part of the machine stays the same, just the right side was changed a little bit to have that mandrel, and the polymer melt will come from here. It flow around the legs. These parts are called leg, and then the mandrel reunite into monolithic tube wall. In this picture, we have the extrusion die for coating wire, and the process is simple. We have a polymer melt that is going to be applied to bare a wire, as the wire is pulled at a higher speed through the die. So the wire is here, and it's going to be drawn this way, and the polymer melt will cover the wire in a vacuum chamber. So that vacuum chamber between wire and polymer promote the adhesion of the coating, and the product is going to be wound into the larger spool at a higher speed. The speed can be 50 meters per second. We have various polymers for extrusion process. Some of the thermoplastic polymer that we use for extrusion are polyethylene, this one, which is the low density PE, and we have polypropylene, we have polyvinyl chloride, we have cellophane. The process that are used for sheet and film production are continuous, and they are very high speed. Some of them are listed here in this slide, and we want to talk about them one by one. The first one is a slit die extrusion for a sheet and film, and blown film extrusion process, and the third one is called calendering. So let's look at the first process, which is slit die extrusion. In this process, we can create a sheet and film by a conventional extrusion process, and it has a narrow slit, which is somehow a die opening, as you see in this picture. If you look at the cross section, it has a manifold, and the manifold spread the polymer melt laterally before it flows through the slit. Okay, and the slit might be up to 3 meter. It can extend up to 3 meter or 10 foot wide, and can be narrow around up to 0.4 millimeter. And there is one problem in this process. It's a uniformity throughout the width of the stock, because there is a drastic shape change of the polymer melt. It becomes one concern. Normally they trim the edges, this area, once the part is made, because that area is a little thicker comparing with the inside of the product or the sheet. The next process is called blown film extrusion process. It's a complex process. It combines extrusion and blowing to produce a tube of thin film, and it is mostly used for making thin polyethylene film for packaging purposes. As you see, this picture shows the process sequence, and the extruder is here. We have air that is going to be blown into inside that tube, and we have a frost line in this area. That frost line marks the position, and it shows that where the solidification of the polymer occurs. And we have air inside the tube. In this area we have air, all of them. And then there is a pinch roll up there. This is 2 pinch rolls that squeeze the tube back together when it is cool. And there are some guide rolls and collapsing rolls, which are used to restrain the blown tube and direct it in toward the pinch roll. Then the flat tube is gonna be collected by the wind up roll in this section. The next process is called calendering, which is shown in this schematic. We have a feedstock that is coming from the mixer, and it's gonna be passed through a series of rolls to reduce the thickness of that feedstock to a desired gauge. This machine, this system is expensive, but it has a high production rate, and the process has a good surface finish. And typical material are a rubber or a rubbery thermoplastic, and some of the products are a PVC floor covering, vinyl tablecloth, pool liner, and etc. The plastic material are also being used for production of fiber and filament products. And what are the fibers and the filaments? The fiber is a long and thin strand, and its length can be at least 100 times of the cross section. So this is the fiber, and it has a cross section. So the length and the area, it has to be more than 100. Filament is the fiber of continuous length. So it doesn't have a discrete length. It's continuous. Here are some of the application of the fiber and filament. It can be used for textile, and it can also be used for reinforcement material in polymer composite that we talked about in the chapter 7, and it has a lot of application. It is growing. The material that we use for fibers and filament, there are two categories. One is natural and one is synthetic. For the natural fibers, um, we have cotton and wool. Wool is less common comparing with the cotton material. Also, we use synthetic fibers, which can include 75% of the total fiber market. And some examples of the synthetic fibers are polyester, nylon, acrylic, and rayon. One of the process for fiber and filament production is called spinning. We use spinning for synthetic fibers, and it is simply extrusion of the polymer melt or solution through a spinneret. Then we're gonna draw and wind it onto a bobbin. A spinneret actually is a die with multiple small holes. In the next slide, I have a picture that shows the spinning process. We have three variation depending on the type of polymer. One is melt spinning, one is dry spinning, the last one is wet spinning.